Welcome to lesson 5.3. Today we're going to talk about the ideal gas law. The ideal gas law is actually derived from a combination of Boyle's, Charles, and Avogadro's law. The ideal gas law is pictured here. The P, as in all the other gas laws, stands for pressure. V stands for volume. N is a new, well, actually, N is not new. N is for moles, as it is in most chemistry calculations. R is something new. And then T is your temperature in Kelvin. So R is what we call a proportionality constant because we know that PV is proportional to NT, but we need to add a proportionality constant to actually make them equal. And so we have R, and it's important when you look at R to notice the units that come with R. This is the gas constant that is used most often. If you do manipulate some of these units, you will get a different number, but we try to make sure our volume is in liters, our pressure is in atmospheres, obviously our temperature is in Kelvin, and our N is always in moles, so that we can use this particular gas constant. The equation of state for a gas, where the state of its condition, what is its condition at any given time, is what the ideal gas law is. So the ideal gas law is it's not for a change in what happens to a gas, it's to figure out a variable when you have a certain set of conditions. So if you have two different volumes, you don't use the ideal gas law. Two different pressures, you don't use the ideal gas law. You'll use something called the combined gas law. And this particular PowerPoint takes you through and has you using the ideal gas law for each of those problems. But it's more like they're using the combined gas law because, certain things are held constant. And I'll talk you through that as soon as we get to those slides. The ideal gas law is based on experimental measurements of the properties of gases, and the gases that obey this law are said to be behaving ideally. An ideal gas, a truly ideal gas, it does not exist. It's just simply hypothetical. But it's much easier to do the calculations in a general chemistry course if we assume that. So gas law problems we can have, if we have conditions that are changing, we could use Boyle's law, Charles' law, or Avogadro's law. But if we're using the ideal gas law, we have one set of conditions. So let's jump into this. Suppose we have a sample of ammonia gas with a volume of 7 milliliters at a pressure of 1.68 atmospheres. It's compressed to a volume of 2.7 milliliters at a constant temperature. Use the ideal gas law to calculate the final pressure. So in this particular example, what you're given two volumes and one pressure, and you're asked to calculate a pressure. I wouldn't use the ideal gas law on this one. I would simply use Boyle's law. And so although these next few slides are going to take you through how to use the ideal gas law, I don't know why we would want to make things more complicated than they are. Because in this instance, we don't have to change units. We can leave them the same. So the initial conditions, we have a pressure of 1.68. We have a volume of 7, and we can leave it in milliliters. What's the pressure going to be? So what is our pressure going to be if we compress that particular ammonia gas to 2.7? So if we take 1.68 times 7, and then we divide that by 2.7, we come up with a pressure of 4.36 atmospheres. And so we just use Boyle's law to do that problem instead of using the ideal gas law. There are some problems where you'll have to use the ideal gas law, but like I said earlier, why make it more difficult than it is? So let's look and see what they have on their slides and see that they came up with the same answer. There we go. They just rounded it to 4.4 atmospheres. So through all that derivation, basically they did the same thing we did. We used Boyle's law. Now let's look and see if our answer makes sense. Since we decreased the volume, we would expect the pressure to increase. That's what our calculation indicated. Just a short little statement here. Most gases do not behave ideally above 1 atmosphere, but that's because you're forcing them to be closer together than they want to be. So if we actually did this experiment, our pressure wouldn't be exactly 4.4, but it would be close. Excuse me. All right, again, a sample of diborane gas, a substance that bursts into flame when exposed to air, has a pressure of 345 torr at a temperature of negative 15 degrees Celsius and a volume of 3.48 liters. If conditions are changed so the temperature is 36 degrees Celsius and the pressure is 468 torr, what will be the volume of the sample? And so again, they're going to try to take you through the ideal gas law to do this calculation, but you are given one pressure, another pressure, one temperature, another temperature, one volume, and then you're supposed to solve for the other volume. We can use something called the combined gas law, and what it does is it takes Boyle's law and Charles' law and puts them together. So P1 V1 over T1 equals P2 V2 over T2, without having to use the ideal gas law, without having to change anything except for our temperatures. So let's go ahead and change our temperatures. That negative 15 will be 258 Kelvin, and that 36 will be 309 Kelvin. And so let's plug them in. Our initial pressure, 345 torr. So see, we don't have to change any of our units. Volume is 3.48. Initial temperature 258 equal to 468. We're trying to solve for volume, and our second temperature is going to be 309. So on this, what you're going to do is you're going to cross multiply. So what I'm going to have is I'm going to have 345 times 3.48 times 309. And then when I cross multiply here, I end up with these two numbers, the 258 and the 468. So I'll have to divide, and I'll have to do that with parentheses. So all those numbers I had before divided by parentheses, 258 times 468, close my parentheses, and that's going to give me a second volume of 3.07 liters. Okay. What did I do to the pressure? I increased the pressure, so that would mean my volume should decrease. That's what looks like happened. But occasionally you'll have some issues with temperature. Temperature, what did I do? I also decreased the temperature, so that's going to cause not quite a big a change in volume. So let's see what they do with the ideal gas and see if they come up with the same answer. So there's that combined gas law that I showed you. Yes, they got 3.07 liters. Okay. So again, walk through that if, go back through that if you need to. Look at the PowerPoint slide that I have on the Canvas site as well. A sample containing 0.35 moles of argon gas at a temperature of 13 degrees Celsius is at a pressure of 568 torr is heated to 56 degrees Celsius and a pressure of 897 torr. Calculate the change in volume that occurs. Notice on this one we do have moles are given, but the moles don't change. And so we do have two different temperatures, we do have two different pressures, and it's asking what our change in the volume is. So we are going to have to calculate what our volume is initially. So we will have to use that ideal gas law to calculate that initial volume so that we can calculate the final volume. So notice in this particular data table, they have indicated the number of moles initially and at the end. They have changed both pressures to atmospheres by dividing by 760 torr, and they have adjusted both temperatures so that they're in Kelvin by adding 273. So first we're going to solve for V1 by using the ideal gas law. And so P1, or pressure volume, equals nRT, or as the Chem 2 students often say, PVnRT. Moles, there's our universal gas constant, temperature in Kelvin, and then that's the atmosphere. So this is the initial conditions. We end up with having an initial volume of 11 liters. So then we're solving for volume 2, we can actually use those conditions as well to solve for volume 2. So again, we're just simply using the ideal gas law in this case to solve for the second volume. We could have solved for the first volume and then used the combined gas law to solve for the second volume. But the change in volume, it went from being 8 liters to from being 11 liters to being 8 liters. So this change in volume, it went down by 3 liters. All right, so we're going to finish up this PowerPoint presentation by going through and kind of conceptually looking at some different graphs and seeing if we can figure out the relationships between these two. So the first one is looking at Boyle's law. So this join in 4 is looking at Boyle's law. Pressure versus volume. So pressure versus volume. What happens to pressure when you increase the volume or vice versa? So these two are inversely related. When one goes up, the other one goes down. And so as the volume increases, then the pressure should be decreasing. And so you're going to get, the only one that goes negative is E. So that is your graph of pressure versus volume. Join in 5 is a question about 4 different gases. They all have the same volume at the same temperature and pressure. And with gases, if they have the same volume at the same temperature and pressure, if you were to calculate using an ideal gas law, you would also know that they have the same number of moles. And so if they have the same number of moles, that means they have the same number of molecules. And so those are all the same. So if you need to, please pause the video and process these as I go through them. Number 6, we're looking at number of moles versus temperature. If you if you increase the number of moles, so if you look at PV equals nRT, so what we need to do, these things are equal on both sides. So if I increase N, what has to happen to T for it to stay equal to this? So if N goes up, T has to go down. So again, this is an inverse relationship, and E is going to be your correct response on that one. Join in 7 talks about volume temperature. This is Charles's law, or again, you can use PV equals nRT to look at this. If volume goes up, temperature goes up, because we need to keep the sides of these equations together. And so your correct response on this one is going to be A. You're going to see here, because if volume is 0 and temperature is 0, you do hit the axis. So that's why you choose A over D. Okay. Join in 8. Join in 8 is volume temperature. So where are these in the ideal gas? If volume goes up, temperature is going to have to go up on this one as well. But notice this is Celsius. So this is actually going to be here, because you can't have, when you do volume and temperature in Celsius, you don't have an absolute 0. Number 9 is volume versus moles. So PV equals nRT. If volume goes up, what happens to our number of moles? Well, it has to go up in order to keep the sides of these equations equal. So again here, it can go through the axis, because if you have 0 number of moles, you should have 0 volume. Join in 10 is pressure. This was kind of a different one. You're plotting pressure volume versus volume. And this particular one is going to, since this is inversely proportional, so every time we increase the volume, the pressure has to decrease. That means it's going to be a constant, because as volume increases, then pressure is adjusting, and so that's always going to be held constant according to Boyle's law. Join in 11. This is, which of the following graphs represents a plot of PV versus N for an ideal gas at constant T. On this one, if I have PV, so if N is increasing, PV also has to increase. So I would have to say that this one is answer choice A. I'm not sure how much of that graphing shows up on the exams or the quizzes, but that is a kind of a conceptual issue. So if you can step back and process things like that, chemistry is a lot easier to understand. So this concludes lesson 5.3. The next lesson in 5.4 is going to be gas stoichiometry. So we're going to use these principles that we've learned, and we're going to be able to figure out the number of moles that we'd get if we mix A and B together. Okay.